Hello and welcome to Lecture 9 of Traffic Econometrics for a master student. In this lecture, it's all about inferential statistics of discrete choice models. So we will start with the best method to calibrate discrete choice models, which is the maximum likelihood estimation. We will also show that we could even use it for the regression models. Then we will, as in a regression case, calculate the variance-covariance matrix of estimation errors, because this is needed for doing inferential statistics. And then we will use some significance tests, which are basically the same as in the regression model case, so we can get a little bit faster about this topic. And also with goodness of fit measures have some in parallel of regression models. In regression models this would be R squared and such things. So let's just go to the maximum likelihood estimation. What does this method do? One calculates the likelihood, that means the probability, that the model correctly predicts all the data, and that's the likelihood function. In discrete models, such as discrete choice models, it's easy. We can use this probability direct. So with likelihood is the probability that the model predicts all the outcome of the first observation, of the second observation, until the nth observation, which is decision in this case. And then we maximize this likelihood with respect to the parameters beta, giving rise to a nonlinear optimization problem. So that is the case for discrete models such as discrete choice models, but we can also use the maximum likelihood for continuous models, that means continuous endogenous variables. There, instead of a probability, the combined probability, we just take the combined probability density. That means that it's a multi-dimensional probability density, that probability that the density is at the data points is maximized. Of course, one should verify that the formula for the continuous models, that means the probability density will be maximized, is equivalent for the discrete models, where the probability itself will be maximized. For this, we assume, as one usually does with probability density, that in a small interval around a given value of y, what is the probability? That's basically just density times this interval, and in multi-dimension it's of course when the density times the multi-dimensional volume element around this given values of y. If one keeps the volume element constant, then that means the differential probability will be maximized, and thus the probability will be maximized. So this is more or less equivalent. So the actual estimation is to maximize this likelihood function. That's the name derived from maximum likelihood method. So the calibrated set of parameters is just the argument that maximizes the likelihood function with respect to the parameters. Often, however, one does not maximize the likelihood, but the log likelihood. That means one just takes the logarithm of the likelihood, which I call tilde L from beta, is just the logarithm of likelihood of beta. Of course, one might wonder, why is this equivalent? Is it equivalent? For this, you have to observe two things. First, as a probability or probability density, the likelihood is positive. At least it's not negative, but usually it's strictly positive. And the logarithm is strictly monotonously increasing in the area of 0 to infinity with 0 excluding. So that means we just apply a strictly monotonously increasing function to the likelihood, the logarithm, and of course, if it's really strictly monotonous, then the inequality x greater than y is then and only then valid if f on x greater than f on y. If f is a strictly monotonous function, for example, the logarithm of an exponential function, anything which is strictly monotonous. And since the maximum is based on such inequality function, that means the argument of the maximum remains unchanged. Of course, the maximum itself will be completely different, but we only focus on the argument of the maximum, and this remains unchanged. And why do we do it? We will see it when giving some examples. And the first example, the first application is regression models, and we will show if the question is, can we also apply the maximum likelihood to regression models? And if so, does it give the same result under which conditions? So let's just do it. Regression models are continuous. That means we need the probability density. The multi-dimensional probability density is because the stochastic terms of the regression model according to Gauss-Markow, they are IID normal distributed with expectation 0 and a constant variance. Particularly, they are independent, and if they are independent, the multi-dimensional probability density is the product of the single probability densities. That's why we can write it first in this form, the likelihood function. Now we assume that this epsilon is not only independent but also identically normal distributed, and then just insert the famous bell curve for the Gaussian density. And this yn is the outcome of the nth decision. That means typically it's the nth person, the nth decision maker, and this is the model with the parameters which are then maximized. Not the decision, because we are regression, sorry, it's just the nth data point, and this is the nth model. So the product and exponential function and all that is cumbersome to take derivatives of, so that's why we now apply the logarithm. The logarithm product reverts to a sum. So that's just inside the product we have a sum and the logarithm of this f. And the logarithm of this f is just taking the usual logarithm rules. For example, 1 divided by the square root gives a prefactor minus 1/2. And that the product gives a sum of the logarithms, and the exponential function gives just the exponent itself. So this is and now we can simplify it a little bit. So the first term, this is constant, so we just can multiply it with the number uppercase n of data points of the observations. We just get this constant term, which of course drops out if you take derivatives. So this is not really relevant. What is relevant is just this term. And this is just, you see, the sum of squared errors. This was the sum of squared errors. You could also see it here, the sum of squared errors. Sum of squared errors. The only difference that there's prefactor 1 divided by 2 sigma squared. However, sigma squared is constant and positive, so when maximizing, this drops out and this additive constant drops out as well. That means we have equivalence between the sum of SSE for the least squared errors calibration and the maximum likelihood calibration is equivalent if the random terms are IID normal distributed. Okay, but we had already as a product, it's just because they are independent. It's just for to make sure that you understand it. So now the proper application is of course to discrete choice models, because we can apply the maximum likelihood to regression models, but we cannot apply the least squared error methods to discrete choice models, to discrete models. So here the maximum likelihood method is the only a possible way to calibrate a model, that means to estimate the parameters. Here, because being discrete, we have no probability densities, but the probability itself, which will give a likelihood function. First, we start denoting the probability for a single decision. And this, of course, the output is the decision vector. It's just one at one decision, at one alternative and 0 for other alternatives. So it might seem cumbersome to write it in this complicated way, but we will see later that in some cases this expression is to be more elegant even than the other expression. We will now use both. So that the probability that the probability for the first is equal to the data and so on, and only one element of the data is 1, because we know the choice set is exclusive and complete, that exactly one of these y, which are the chosen alternatives, is 1, all the others are 0. So that was for one choice. However, we want, of course, calibrate the models to all the data. That means to all the choices taken and which we now give to the model. So that means the likelihood is a probability that the first choice gives the first data output, the second choice gives the second data output, and the nth choice gives the n data output. And if we first, because they are again independent, because the random utilities are independent from one decision maker to the next, that means we can have a product of the probabilities for each single decision, and that is just taken from above. So we have a double product in this way. Again, it's cumbersome to derive, to take derivatives of products, so we use the logarithm. And that's the result, the maximum likelihood estimation. The estimated set of parameters is the argument of the maximum of the log likelihood function, and this log likelihood function is just the logarithm of this likelihood. The products revert to sums, the power function returns to a single factor, and this probability will be a logarithm of probability. And here we use also the other form, because we know only one of these y is, for each decision n, only one of this y and I equals 1, and all others are 0. That means this inner sum just vanishes, and instead of I we have just the decision, the taken decision at the decision n, the taken alternative at the decision n. And that is just the log likelihood function, which is being maximized when calibrating parameter. So show that in deriving this main maximum likelihood result, that means this result, the random utilities need not to be uncorrelated between alternatives, only between choices. That can be seen first, it's only uncorrelated between choices. That means the outer product can be written in this way. And for the inner sum or product, we know that only one, the data value of only one is positive. So it does not matter if there are some inner correlations. In any case, we can express it in this form. Of course, the probability itself, the model probability, that of course depends on assumed correlations in the of random utilities. But the form is the same, whether they are correlated between alternatives or not. Yes, that's basically the answer. So now we start with the first application, just estimating a model with only alternative specific constants. So if we have uppercase I alternatives, you know from the last lecture that we have I minus 1 alternative specific constants to completely specify the ad hoc utilities of the choice set of alternatives without any real exogenous variables. It just takes into account the ad hoc preferences of the decision makers. You can write it in this form as a sum of delta functions. You can also write it in this form. That means the utility of alternative I is just beta, unless I is the last alternative, because then it's 0, because the last alternative uppercase I is the reference alternative. So these two expressions are equivalent to this expression. So how can you show that the estimated model just gives probabilities that are equal to observed relative frequencies Ni divided by n. Ni is the sum of all decisions for alternative I, and n is of course the total number of all decisions. And because there are no real external factors, that means this model does not depend on n. That means it's the same for all decision makers. That's why we do not need to express the maximum likelihood calibration with respect to the betas, but we can also directly look at the probabilities. And here the result is that the calibrated probabilities are just the same as the relative frequencies of this, just the ratio of the actually taking decisions. That means we need to minimize the maximum likelihood function or the log likelihood with respect to the p vector, satisfying the sum condition that the sum of all probabilities equal 1. And if you minimize something or maximize something with restraints, the proper way to do it is using Lagrange multiplicators. We will see how this works. So first the log likelihood function. In this, the first is the sum over all decisions, the logarithm of the probabilities at the taken alternative in the data. And this because the probabilities do not depend on n, but only on I. We can reformulate the sum not as a sum over n, but as a sum over alternatives with uppercase Ni persons actually choosing each alternative, and then just the logarithm of the probability. And that's the thing which is to be maximized under this constraint. You do it just to take a derivative of the unconstrained function minus the so-called Lagrange parameter multiplied with a restraint in the form restraint equals 0. Sum pi equal 1 is of course sum pi minus 1 equals 0. And this is just derive, taking the derivative with respect to pi. That of course gives n logarithm n, that's just n divided by p, that's and the restraint taking the derivative is just the Lagrange multiplier itself. That means probability is proportional to the number of decisions taken, and that of course means, because the sum of the probabilities is equal to 1, that means that probability is the number of decisions for alternative I divided by the total number of decisions. Then of course, once we have the probabilities, we can also calculate the parameters itself. For example, for the logit model, we have Ni divided by, I just take the ratio to the reference alternative because that's just exponential of beta I. And that of course can be resolved to with respect to beta I, which is just the logarithm of the ratio. For the probit, it's similar. Where we will get some quantiles for the probit one. So now we come to a real exercise with actual exogenous variable. In the simplest possible case, binary decision, pedestrian and bike. So for some short errand, for example, go to a bakery, do I walk or do I use the bike? Because it's so short, other means of transport are not relevant here. So we have just one alternative specific constant because we have two alternatives, and we have because both pedestrian and bike have the same appraisal for time, so we have just a global time sensitivity times the complex, the house door to house door travel time. And these are the data. The data are taken from, no, these are just there's not from any real experiment, I just invented them. So they are basically stated choice data. And if you just, because we have only two parameters, we can just plot the log likelihood directly, graphically, because it's just a function of two variables, beta 1 and beta 2. And here you see how it looks like. Obviously, you see there's some distinct and unique minimum. That's a log likelihood. Of course, it's always negative. And this minimum, the argument of this minimum is just the sought after parameters. By the way, you can show that for logit models, if you have linear deterministic utilities, then you will always have a minimum exists and it is unique. That means when the calibration is unique. So how do you proceed? Let's do it first for the logit model. Just find the minimum. That's basically the minimum is about here, at least given from a graphical. So it's just the minimum. So this is a sort of valley, and here's the minimum of the valley. So it's about at the log likelihood of minus 12. Beta 1, that's here, it's about minus 1.3 or maybe also 1.35. Beta 2 is minus 0.14, so this is 0.15, that is 0.1. So these are the maximum likelihood estimation, can be done directly graphically for this case. That's, by the way, also something which is a good problem for oral tests and maybe also for internet tests. So now we do the same for a probit. One sees that we're really, because it's an IID probit, so it's just identical standard normal distributed utilities. We see about the same log likelihood. That means the overall fitness of this model is basically the same as this. The parameters are a little bit different. They are smaller here, but both beta 1 and beta 2 are smaller. Why is this so? That's because the random utility here has a standard deviation of 1, And here the Gumbel distributed random utilities have a standard deviation of pi divided by square root 6, which is about 1.28. So it's expected that these are smaller by this by division by this factor. Not exactly, of course, because it's a different model, a different random utility, but typically if you have IID probit models, you always get similar results. That's why you do not use them at all, because these can be calculated more easily, and probit models are restricted to cases where you want correlation structures. Of course, generally you cannot do it graphically because you have more than 2 parameters. So generally we have a nonlinear optimization problem, and there are, I just give a list of methods. You do not need to know these methods by heart. Just there are classical ones. This gradient method is slow but reliable. This Newton is very fast but is also unstable. Then there are some methods which combine the velocity of the Newton method and the stability of the steepest descent methods. And if you are a very complicated optimization landscape, then you can also use genetic algorithms. For each of these methods, there are toolboxes which you can use more or less out of the box. Interestingly is the multinomial logit model. In the script I've derived the conditions for the general multinomial logit model. You do not need to redo these derivations, but it's instructing to do so. Anyway, what is the result? The result is very instructive. The model is calibrated if all property sums agree between the theoretical predicted property sums and the data ones. The theoretical one is just the corresponding factor, exogenous factor m, which is related to a parameter beta m, and that's of course summed over all decisions n and also over all alternatives I. Here of course we need to do really the sum, because here it's just for each alternative the discrete choice model will give some finite probability. On the right hand side is the data realization. That is just the realized sum of the properties, and here of course we can get rid of the inner sum, because by means of this unique and complete decision we have only exactly one decision which is taken, and this is just the alternative I n for the decision n. And so for each parameter beta, these two property sums need just to be the same. Maybe some example. We have a situation, 2 alternatives and 4 factors. First we have a generic time sensitivity, a generic cost sensitivity. Then we have a gender preference for alternative 1. And we have the general preference, which the general alternative specific constant. That means the reference alternative is 2, and the gender has the usual dummy, male equals 0 and female equals 1. So we have 4 parameters, that means we have 4 property sums. The first property sum is just the total time. The total time modeled is just the sum over all decisions and all alternatives, the model probability as a function of beta times this time of this for decision n at alternative I. At the data you just sum up the travel times of all realized decision, only a realized one. With a cost it's basically the same. What is the case for the gender? Maybe first the realized one. The realized one is just the sum of decisions for alternative 1 because this is delta I1 taken by woman. That is the realization, and in the model it's just also only the women are taken care of, gn equal 1 for main. The men are neglected because here with g the dummy is 0, and so we have also the corresponding modeled decisions. Finally, the alternative specific constant itself. Here it's not the female decision makers choosing alternative 1, but only but all decision makers. It's just the sum of all decisions in favor of alternative 1. And of course here it's the sum of all the probabilities for alternative 1 over all decisions n. This finishes the actual parameter estimation using the maximum likelihood method. However, we are not yet done, because the values of a parameter as such are not of much use if we do not know how reliable the estimation is. What are the errors of the parameter estimators? It's just the same as in the regression models. So we need also the errors in terms of variances and covariances. Only then we can do the classical inferential statistics. So let's just do this. Estimating the variance-covariance matrix. For this, remember that the maximum likelihood method implies that at the value beta hat beta, at the estimated values, the gradient of the log likelihood with respect to the parameters is 0, because otherwise there is no extremum, and in this time a maximum. That means we can write the log likelihood as a sum of the Taylor expansion. First term is just the maximum likelihood itself. The first term, the gradient term, vanishes because of this condition, and the second term is just it's a generalization from one-dimensional case, where the second term would be 1/2 times second derivative times change of squared, and in a multi-dimensional case the second derivative is just replaced by the Hessian. The Hessian is the matrix of all mixed partial derivatives. That means the diagonals is just the second derivatives with respect to beta m, and the off diagonals are the mixed partial derivatives. So it's just the normal Hessian. So this expansion can be done because we are at the calibration point. So how does this help us? First, we go back to the, not to the log likelihood, but the likelihood. That of course is just the exponential of the log likelihood. So we have, instead of additive terms, we have multiplication. Or that's why we Lmax, that's the exponential of tilde Lmax times this exponential. And now we compare this likelihood with the multidimensional Gaussian, because for this multidimensional Gaussian we know all the variances, covariances and correlations. And the multidimensional Gaussian is defined just for a vector x. It's just some prefactor, which is not interesting, times the exponential of minus 1/2 when x transposed inverse of a variance covariance matrix times x as a normal column vector. And now we identify this expression with this expression. Of course, with prefactor Lmax, and here this prefactor is irrelevant, so we only need to identify the exponential, that is exponent. That means you see what will happen. this is what we thought, the variance-covariance matrix, and this is what we get, the Hessian. So it's easy just to express the variance-covariance matrix in terms of this Hessian. And that just gives the result. The variance-covariance matrix of the beta estimators is just the inverse Hessian at the calibration point and minus. It's also obvious that there must be a minus because we are at a maximum. That means the second derivatives are negative, or more precisely speaking, the Hessian is a negative definite, but of course the variance is positive definite. That means we need to multiply it by -1, but it can also be seen here. Here's a minus and here's no minus, so one minus must be here. And this is a very essential result, that it's very easy to get the variance-covariance matrix, just calculate the Hessian and invert it. We can also show that this seems that under these conditions the maximum likelihood method is even efficient. For this we just revert we relate the inverse of the variance-covariance matrix with Fisher's information matrix. In a way, the more precise your data are, the more information you have. So that's just quite plausible that the information matrix is sort of inverse of the variance-covariance matrix, giving all the uncertainties. And now there's a important general result that a lower bound of the variance-covariance matrix is the inverse of this Fisher's information matrix. And however, in our case, we have just this Fisher's information matrix. That means the maximum likelihood estimator is asymptotically efficient. One can even compare the variance-covariance matrix with that of the regression models, because there is also Hessian, the Hessian of the second derivatives of the sum of squared errors. And apart from a factor sigma squared, it's basically the same. So let's just apply it to the already known in-class survey. It was the stated preference survey where we had three alternatives. We already have shown this output, but that was just descriptive. Now these are just the values, and now we have also this plus minus, and this plus minus are just the diagonal elements of the square root of the diagonal elements of the variance-covariance matrix. And if you plot the likelihood here and the log likelihood itself, you see that that there's a unique maximum. Here it's because we have more data, it's -100, maybe -141. You also see that very near the maximum you have a sort of elliptic shape. This elliptic shape means the second order term characterized by the Hessian is enough. However, here you see that it somewhat gets distorted, and if you get to this regime very large errors, the so-called asymptotic expansion, where you only which is only valid if you have much data, breaks down. But when everything becomes very, very complicated, corresponding to a student t-distribution instead of Gaussian for the regression case, we do not consider that. So we always assume that we are in this inner regime where the second term of the expansion is enough, and that means the estimation, the maximum likely estimation, is then also Gaussian. That was just a section for two parameters. With all the other parameters, beta 1, beta 4 equal to the calibrated value. And here you have a whole a matrix of two-dimensional Gauss sections. And you see there's a very nice, unique maximum with respect to all dimensions. We can also do this by another survey I did in the audience, the revealed preference survey. That's actually the realized choices for your means of transport at the way from home or wherever you went, wherever you originated to this lecture. First, of course, I surveyed the distance in distance classes, and then I surveyed that for the smaller distances, most people choose pedestrian or bike, and for a bigger distance, of course, the faster means public transport or car. How to model this? It's a sort of special because I have no individual decisions. Just for economic purposes, time purposes, I surveyed one distance class simultaneously, just by raising the hands. So this is a sort of way, it's an attribute not of a decisions but only of a person, so it needs to be, the distance needs to be alternative specific formulated. Although it's in reality, it's also more person-like attribute, because whether you use pedestrian, bike or public transport or car, the distance are about the same. So a model is just here, it's just written out for each alternative. So it's just this distance r is just modeled in an alternative specific way, and the variance, the utility 4 is the reference with 0 utility, because it's just everything is related to this alternative 4. And these are the calibrated parameters. Here you have 6 parameters, and here you see the model, that is the curved line with a maximum likelihood calibration, and you see here it fits pretty nicely the data. Again, just plotting the two-dimensional intersections of the multidimensional likelihood in a parameter space, we get a unique maximum. Now, where we have both estimated values and also the variance and covariance, we can go into the inferential statistics of discrete choice models, which is part 3 of this lecture. As I said, the procedure is pretty much the same as in regression models. With the difference that we always assume the asymptotic case. That means we are near the, we have comparatively many data, where also in the regression case the student t distribution reverts to the Gaussian, and the variance-covariance matrix is, we take the estimated value variance-covariance matrix at face value. That means we do not consider second order errors, that means errors of the estimation errors. Then the confidence intervals are just given in terms of the standard normal quantile. It's just the usual confidence interval around the estimated value, and the half with delta, which depends of course on the confidence level alpha, is just the quantile of the standard normal 1 minus alpha half times the standard deviation of the estimated error, which we take at face value. That means as though it is the true error. That's why we could use the Gaussian Z and not the student t distribution t. So that is the confidence interval. The test is completely in analog. You need a test statistic, which is just the deviation from the threshold of a null hypothesis in terms of the estimation error, and this is a standard normal distributed if the actual real value is at the boundary of the null hypothesis. p-values are pretty much the same as in the regression. So depending whether you have a point test, when you have this expression, if you have a less equal test, you have this expression, and if you are greater, then you have this expression. Completely in analogy to regression models. And also as in regression, you need a factor 4 of more data to halve the error. That's because of this square root. Because this variance typically decreases with 1 over n. There's also an analog to the f-test of regression. Remember, the f-test tested nested models, the full model, and restricted model, a restrained model. And this restrained model is just the full model with one or more parameters fixed. That's what we also call simultaneous test. That means a test we tested simultaneously if it's plausible that parameter 1 has value 1 and simultaneously parameter 2 has value 2 and so on. That's in effect just a restrained model, the full model given at the fixed parameter values. Pretty much the same is also available for discrete choice models and for maximum likelihood relay as a total. Again, the null hypothesis says the restrained model MR, that means the model with just R remaining parameters, describes the data as well as the full model. The test statistic here is the LR statistic, and it's just 2 times the logarithm of a ratio. That's why it's called likelihood ratio, because it's just a ratio of likelihoods. Of course, you could also write it, because it's a logarithm, you could also write it as a difference of the log likelihoods. So this is the likelihood of the full model, the maximized likelihood at the estimated parameters, and that is the likelihood at the calibrated restrained model. Formally, this likelihood function is the same as that, only that here all parameters can be varied for minimization, and here only the remaining parameters. And if the null hypothesis is true, then in the asymptotic case, this test statistic is chi-squared distributed, and the parameter of the chi-squared distribution is just the difference of parameters. Full model has m parameters, the restrained model mr parameters, and that's it. Of course, data realization just calculate, and obviously the full model describes the data better if the likelihood is and the log likelihood is much larger. That means the null hypothesis is rejected if this is greater than a threshold value, and this threshold value is just the usual quantile at the significance level alpha, or alternatively the p-value for a greater or greater equal test is just 1 minus the distribution function itself of a chi-squared distribution at the data value of this LR statistic. Let's just do an example for a simple mode choice for the roots of this lecture. There was also a lecture survey, but a simpler one with only 2 alternatives. I just summarized pedestrian bike as the slow alternatives and public transport car as the fast one. And again, I aggregated it to distance classes. Alternative 2 is the reference, and obviously beta 1 is the sensitivity to distance of the alternative 1. It's expected to be negative, because if the distance gets larger, then alternative 1 is less attractive, and with beta 2 is just the alternative specific constant, which is an ad hoc preference for 0 distance, and that is expected to be positive, because at 0 distance you would not like to go to a public transport or to take out your car. So what do you get? This is the log likelihood which you get, and because we have here only two parameters, we can take this LR test directly graphically. The null hypothesis is just the trivial model with zero utilities describes the data equally well as the full model. The null model has 0 parameters, the full model has 2. That means the test statistics 2 times the difference of the log likelihood is t squared 2 distributed, provided that the null hypothesis is true. Now the data realization can be just read off. The data, the maximum likelihood is so this is 28. One line is one log likelihood unit. So we have something like 28 is this. Now this is even 27. So we have this is 27, and maybe this is 26.5. This is the full model, 26.5. This one, and what is for the null model? We have just 0, 0 here, and that is about 35.5, and then you get a value of 18. And now is this the quantile for the common alpha equal 5% significance level is about 6. So it's much smaller than 18, so it's clearly rejected. And in fact, the p-value would be 10 to the minus 5 or so, extremely small, highly significant, which also is shown here. That is the model. That is the faster alternative, which is of course preferred for a larger distance. But it's interesting how well this simple model predicts the data, because these are real data. What would the null model predict? Because the utility is just 0, it's just 50-50. That means both probability for both alternatives is just 0.5, which obviously is a very bad fit. So finally, we come to the goodness of fit measures, which the equivalence in regression models would be the R-squared measure. In contrast to this relative measures, likelihood ratio test, we have here an absolute measure. That means an absolute measure for the fit quality. And that is sometimes also needed, because the relative measures, that's even is a parameter significant or is a restrained model equally well as a full model, relates to significance. And if you have very much data, there may be a high significance, but still little difference. Just the many data make sure that there is a significant. So in addition to significance, we also need to do the effect strength, so-called. That means, is there really also a significant effect? So that usually, if you would only have a likelihood ratio test, you could, for example, use the top-down ansatz, but it will fail, because removing any variable will give significance, so it cannot be removed. But often it's still too complicated, because the effect strength is very small, and that can be tested by this goodness of fit measures. Furthermore, with goodness of fit measures, we can also compare non-nested models, and we get the effect strength. So what are these goodness of fit measures? There are two information-like criteria, AKI information criteria and Bayesian information criterion. The first term is the same. That's the raw information. It's 2 times the log likelihood. And when there's a correction term, it's a sum, because it's logarithm. So would be a correction factor, but it reverts to sum for the logs, which takes into account that if you have more parameters, you have also certain sort of overfitting. And typically with n, the number of decisions should be much larger than with m, the number of parameters to be estimated. So that means basically this whole ratio is basically 1. So we have minus 2 times log likelihood plus 2m, which is the correction term. And here we have the same correction term, but multiplied with a logarithm of the number of parameters. So if you have more than 4 parameters, this gives a higher penalty. And generally, this is to be preferred, the Bayesian over the archaic information criterion. And there's also goodness of fit measures of regression models, and they are equivalent. Here's again what I already said. The Bayes information criterion focuses more on parsimonious models. And parsimonious for human means you do not want to spend money. Here it means, for models, it means you do not want to spend much in parameters. Spare with the parameters, and that's a parsimonious model, which typically is to be favored, because then the danger of overfitting is little. There are two further measures which are more or less related to the corresponding R-squared measures of regression. So with McFadden's R-squared, also called LR index, would correspond to the normal R-squared of regression, and this would correspond to the corrected R-squared in regression, and it's just the adjusted LR index. So here you see that's more or less the rho squared is 1 minus the, in regression, this would be the explained variance, and this would be the total variance. And here's it's pretty much similar, and the adjusted just gives a penalty for the number of parameters. That means particularly the higher the better. In contrast to this information criterion, here it's the lower the better, because this more or less gives the difference, the information difference needed to get from a model information to the full microscopic information, and that means the information loss when modeling is as compared to having the full data. And of course this information loss should be as low as possible, so low values for AIC and BIC are good. However, here it's just a degree of fitness, and here of course high values are good. There's one difference to regression models, however. In regression models, values of rho tilde squared of 0.3 would be pretty bad, a really bad fit. However, in decision models, a value of 0.3 could even, depending on the model, very good, particularly if it has many alternatives. So in this term it's not really absolute, because you can only say which model is better, but also for non-nested models. And if you have really something like 0.5, you could not even do better. At 0.3 is actually a good value, can be seen when we go back to this. So this seems like a really good fit, but it has R squared of maybe 0.3. So this, because here of course, particularly if data are 50-50, the model cannot do better than 50-50, so it gets many decisions wrong just by force. So finally some intuitive questions on the goodness of fit matrices. First, all these goodness of fit measures are compared either with a null model, that means a model without parameters, or an AC only model. And just think of weather forecasts and the information you have to predict the weather of tomorrow, and compare just as a sort of analogy the trivial model, the AC only model, and the full model. The trivial model would be, given that you can only predict good and bad weather, just 50-50. The AC only model gives, you can use the climate table. For example, if you predict the weather tomorrow in the desert, then the climate table says probably tomorrow is a nice weather, and you can take this information. And the full model would be just having access to a weather forecast, and obviously the information are different. And here are some calculations which you can do at home. As always, I give this lecture notes also in terms of a PDF, so you can just check. I also gave the answers. The answers are always in sort of blue and the questions in orange. And here I have particularly an example that a model which perfectly predicts 3.1 and 1-3 preferences in certain decisions situations still only has an R-squared value of 0.18, which and although this looks very low, it's not so bad. So unlike regression models, the numerical value of this R-squared is not a good hint often, and often rather low values are denote a quite well model, but in any case it's valid that the higher the better. So this was lecture 9 on traffic econometrics. Many thanks for listening.